Chapter 3, Describing Data Using Numerical Measures. So make sure to follow along using the Chapter 3 Practice Problems worksheet. In this video, we'll learn how to compute the range, interquartile range, variance, and standard deviation. So recall in the previous video, we discussed measures of center and location. In this video, we'll be focusing on measures of dispersion or variation. When we're describing data, we're actually looking for the spread. When collecting data, we'll notice that the values of our variables of interest will take on different values, and when we plot them, it spreads around the center. So we want to see how the spread occurs. Variation occurs in everything we do because not everything is going to fall with the exact same number. It's going to vary depending on a variety of factors. And so when we're measuring variation, it's giving us information about our spread or how different they are from each other. When we have a smaller value, that means there's less variation, and when we have a larger value, that means we have more variation. So as you can see here in the diagram on the right, we've got two shapes that represents our spread. So here with our taller curve, where it's tighter or narrower, that means there's less variation because the values that we've collected are much closer together. Whereas our wider curve here has greater variation because the numbers we collected are spread out farther from each other. So one measure that you might want to calculate is the range. To calculate the range, we take our largest value, or the maximum value, and subtract the minimum or smallest value. It's the easiest form of measurement, but the downside is that it is very sensitive to extreme values. So if you have a very large number or a very small number, but the majority of your data is somewhere in the middle, this range will get skewed. It also ignores how the data is distributed, or the shape. Another type of range that we might want to calculate is the interquartile range. So recall you learned how to calculate the first and third quartiles. To get the interquartile range, we're taking the difference between the first and third quartiles. So here, if this looks familiar, this is a box and whisker plot where we have our first quartile at 30 and our third quartile at 57. And to get the interquartile range, we'll subtract those two numbers, and that's our distance between the two quartiles, which is 27. So as you can see, it focuses on what's going on in the middle and ignores the extreme numbers. Another form of variation that we're going to use often throughout the semester, so it's very important we get a good understanding of it, is the population variance. So this is the average of the squared distances of our data values from the mean. So here we have our formula using various Greek letters. So let's make sure we understand what each symbol means. So here is our mu, this is our population mean. Our big N tells us our population size, and our sigma squared here is our population variance. So what you're going to do in the formula here is follow our order of operations. So we'll take each value that we're working with, so here's each of our x's, and we will subtract our mean from it. And for each of those values, we will square it, and then for each of those values, we'll add them all up, and then we will divide it by our population size. There's also a shortcut formula here, but I generally don't use it. I prefer to use this one right here, so see what works best for you. You're welcome to use this if you prefer. Now, with our population standard deviation, it is our most commonly used measure of variation. It's actually the positive square root of the variance on the previous slide. So that's this formula right here you just saw. So to get our standard deviation, you'll square root the variance. And this will allow us to have the same units as our original data. In other words, our standard deviation is going to be in whatever numeric format our story is about, whether it's money or age or weight or whatever data we're looking at. So let's go ahead and work on problem 26. The following data here reflects the number of times a population of business executives flew on business last month. So imagine this is a small company and it only has 6 executives. So that's why it would be considered a population, because that's all the executives we have in our entire company. So to compute the range, you're going to take the largest number and subtract the smallest number. So looking at our data set here, the largest number is 9 and the smallest number is 4. When I subtract 9 minus 4, that means my range is 5. But as we know, the range is a simplistic form of variation, not very useful. So then let's actually look at B. We're going to compute the variance and the standard deviation. So what we first have to do is to get our mean or our average. So as you recall, to get the average of something, we'll add up all of our numbers and divide it by how many numbers we have. So when I add up my flights for my business executives, I get 35. And our big N, or the population size, I can count. I've got 6 numbers. That means I have 6 executives in this company. And then when I divide the two numbers, I get a mean of 5.833. Let's go ahead and now compute our variance and standard deviation. Now, I suggest using a table to help organize our calculations, and you can see this on your worksheet. And so the first thing we want to do is figure out that our big N right here, our population size, is 6 because I have 6 data points. And so these 6 numbers here were just the number of flights from our executives from the last slide. Now, using our formula right here, it's going to ask us to work through the order of operations. So PEMDAS, parentheses first. So what's in the parentheses is I'm going to take each of our x's here, and we will subtract our average, or our mean, that we calculated on the last slide. So here's my x of 4. So this particular business executive, let's call her Susie, she took 4 flights last month, and we're going to subtract the average number of flights for all of our executives. So we get negative 1.8333. We'll do the same thing for our next executive. Let's say it's John. John took 6 flights. We're going to take his 6 flights and minus our average, and we get 0.1667. And we'll continue down the table for each of our executives, taking their specific number of flights and subtracting the average of all of our flights for our executives. Then the next step is to work with our exponents. So we'll take the numbers from this column here and we'll square each one. So that's what this part of the formula right here reminds us to do. So I'm going to take the negative 1.8333 and square it, and I get 3.3611. Note, if you're using a calculator or Excel, you might have slightly different numbers due to rounding or where you decide to cut off. So just be aware that my numbers might differ a little bit from yours. And I'll go ahead and continue down, taking each of these numbers and squaring it. So essentially this column is the squared differences between each executive and the average. Now, the next step we have to do, according to this formula right here, is to sum or add everything up. So we'll go ahead and add up all of these numbers right here, and I get 18.8333. And then for our big N, that was over here, that's our 6, we're going to take our summation right here and divide it by our population size. So taking 18.8333 divided by 6 gives us a variance of 3.1389. Now we're not done though, because the variance is not in our original unit of measure. So in our story, we were counting how many flights these executives took. This number right here does not represent that unit of measure because we squared it. So what we have to do is we have to take the square root of our variance. So we're going to take this 3.1389, plug it under our square root, and then plug that into our calculator, and we get a standard deviation of 1.7717. In other words, we're describing that the variation in flights between our executives is 1.7717. Now, for a sample standard deviation, this is based on sample data selected from the population. Now, if we look at our formula here for the sample variance, instead of a sigma, like you saw for a population variance, you see a lowercase s with a square. That's the symbol for sample variance. And then we have our formula right here. Similarly, our sample standard deviation is simply taking our variance and square rooting it. In other words, we're going to take this formula here and throw a square root over the whole thing. So here in part C, we're continuing on with the same problem. Now we're changing the story. So earlier when we looked at the 6 business executives, we said that was the entire population. But now let's imagine we have a much larger company and those 6 executives weren't the only executives. Rather, it's a sample or subset. Imagine maybe there are 50 executives in that company, but we took a sample of those 6. So we're using the same data points, so we're just changing the way we look at those 6 data points. It's no longer a population, it's now a sample. So here's our formula. And now see this top part here, you actually already figured it out. We took each of our x's, subtracted the average, squared them, and added them all up. So you already did that in the table. I'm not going to ask you to do that again. So that was your 18.8333. You'll notice that the symbol for our mean, though, says sample mean as opposed to population mean, where it had that U or mu sign. Now in the denominator, so the bottom number here in our formula, it's saying to take n minus 1. So our sample size, minus 1. So in our story here, our sample size is now 6, and we subtract 1. And so when I take my squared differences and I divide it by our sample size minus 1, or 5, we get a sample variance of 3.7667. To get the sample standard deviation, I will take my sample variance, throw it under the square root, and then once I square root it, I get a sample standard deviation of 1.9408. Now what you'll notice is that the statistic from our sample, that's our numbers right here, are larger than the parameters which we calculated in part B for the population, because the division for our variance and standard deviation have a different divisor than in the population. Our divisor here is n minus 1. So we're dividing by 5 instead of dividing by 6 like we did in part B. The reason why sample statistics will have a larger variation than our parameters from the population, we're not analyzing all of the data. And so we have to acknowledge that there's going to be more variation. And so that's why you'll see a difference when you compare sample statistics versus population parameters. So now when we compare standard deviations, we can see here we've got 3 different data sets. They all have the same mean, the same average of 15.5, but their sample standard deviations, that's lowercase s here, are different. This sample standard deviation is at 3.338, this one's at 0.9258, and this one's at 4.57. So we can see our spread in data A and C is much wider than that of data B. Data B, all our data points are very close together. And as you can see too, when you compare data A versus data C has more spread because it has more data points further away from the center. So this is why standard deviations are so important, because it tells us how much variation we have going on in our data. And then that will help us when we're trying to make decisions. So if you have any questions, just let me know.